Good morning and welcome back. So far we considered the tangent spaces to a manifold, but only at one point. And only last time we considered the tangent bundle, which is the disjoint union of all the tangent spaces to all the points. Now, it is the tangent bundle and the fact that we saw that it's a smooth bundle of smooth manifolds that now allows us to define tensor fields. And the moment we define tensor fields, there's a little surprise. Because as long as we only considered the tangent space to one point, that tangent space was a vector space. Now we're going to consider not only elements of such a vector space, but in fact sections of the whole tangent bundle, which intuitively can be understood as vector fields, and we will call them vector fields. And it will turn out that we can add vector fields, and we can also scale vector fields. But other than a vector, the vectors in one tangent space, all the collection of vector fields does not constitute a vector space in itself. The collection of all vector fields will actually only be a module. And so today we'll study this connection. So that's 4.7 tensor fields and modules. So unlike mathematicians, most people who apply mathematics consider sometimes rings and modules a somewhat esoteric subject. And today we will see that it's not esoteric at all, and that actually the funny properties of modules that come up, at least if you compare them to vector spaces, are of direct geometric relevance and make us understand the subject better. So that's the reason why we emphasize this. So last time we defined the tangent bundle, and that prepares us for the definition of what a vector field is. Definition. So let M be a smooth manifold, and Tm its tangent bundle. Which we saw as a smooth bundle, so Tm down to M with the bundle projection pi is smooth. That's what we mean by the tangent bundle being a smooth bundle. A vector field, as opposed to only being a vector field is a smooth section of the tangent bundle, and I remind you of what a smooth section was, or what a section was in the first place. If you have a base space M and you have the total space M, there's the bundle map pi that sends you down. That's the bundle. And if the bundle map pi is smooth and M is a smooth manifold, I showed you last time how to construct a smooth atlas, and there's also a problem about that on the problem sheet. But now what if you go in the opposite direction and you call this a map sigma? If the map sigma is such that if you first apply sigma, but then you go back by pi, so you consider pi after sigma, if this brings you back to from where you started, so if this is the identity map on M, then this sigma is called a section of that bundle, in this case the tangent bundle, and the smooth section is simply the restriction that this map is smooth. Now, we already saw before when we talked about sections that if I think locally, a section is can be thought of as to every point you assign a vector, an element in the fiber over that point. So if you have a manifold M and you go to this point P, then this sigma, because of this property pi after sigma is at M, this map assigns to this point not a vector in another tangent space at point Q, but it assigns to this P a vector. So sigma of P is an element of TPM. Okay, it assigns a vector in that tangent space at the point where you are. And that's, of course, the idea of a vector field, that you provide a vector at that point. At another point, you might provide another vector, but it's not that at this point you provide a vector that lies in another vector space. Okay? So this is this section property. Now you can say, couldn't we have had that simpler? Couldn't we have written down a map from M to the tangent space at that point? Well, yeah, but you don't know at which point you are if you start in all of M. And then you have the other problem. You need to say, what does it mean that a vector here, if I have a whole vector field, so that's the intuition of this section, have a whole vector field, what does it mean that this is a smooth vector field, so that you can differentiate and stuff? Well, it's very difficult to say. If you think about this vector at this point, then another vector at the other point, you will have to introduce differentiation of vector fields in a particular new manner, but you don't need to, because if this is a smooth manifold and that's a smooth manifold, we know what a smooth map between smooth manifolds is, right? So that's the basic idea about this definition of vector fields. Okay, so from now on, a vector field is a smooth section of the tangent bundle. That's it. Now, if you look at this, first we call the collection of all such vector fields, call the set of all vector fields. And if I now say vector field, I always mean smooth vector field, because we're on a smooth manifold. You always, I mean, it's as always, if we were only considering topological manifolds, I couldn't talk about smooth vector fields, but I could still talk about continuous vector fields, right? And then I would have a continuous map from the topological manifold M to the then topological manifold Tm, and so on. So at whatever level you are, you can then talk about the corresponding type of vector field, okay? It's always the same thing. I think it's boring to write this down in detail every time. You get the gist of it, right? Okay, so call the set of all vector fields gamma of Tm, which in fact is the standard notation for all the sections of a bundle. So this actually means these are all the sections of the tangent bundle, okay? Again, why is this at all a set, right? Well, we need to say what the restricting set is. But because we define vector fields as maps, we always know how that works. It works always via the Cartesian product and so on. Okay, call the set of all vector fields gamma Tm. So now once we have that, we can actually equip gamma Tm with two operations.
Sorry?
Yeah, sure.
Didn't you say that gamma should go from M to Tm? Shouldn't it be sigma? Shouldn't it be the collection of all sigma?
Yes, the collection of all sigma. So
Then it have to be a M.
no, okay, I know what you mean. So the point is, this is just notation. So this gamma of Tm is called is the set of all sections of that of the bundle with this total space. That's the idea, such that pi after sigma is it M. Clarified, no? Yeah. So that's just notation. If you say the sections of a bundle, you provide here the total space of the bundle. Very strictly speaking, you'd have to say the gamma of the Tm, the pi, and the M, right? Because all of them appear over here. This is just short notation for that. Okay? So that's the set. And now we equip this set with two operations. And now it gets interesting. The first operation is kind of trivial. Let's call it circ+ for the time being. You take two elements of gamma Tm. That means you take two vector fields, not two vectors, but entire vector fields on your manifold, and you map them to a new tensor vector field on your manifold, and you do this pointwise. So there's no big secret. So one is called sigma, the other one is called tau, and you map this pair to something we call sigma circ+ tau, and sigma circ+ tau is defined pointwise. That means at every point of the manifold, P and M, we define this as sigma of P plus sigma of plus tau of P. And where does this guy send us? It sends us to the tangent bundle. but this is just a collection of all the tangent spaces. If I'm at sigma of p because of the section property, this must be the plus in TPM. Okay? So in this sense, point-wise, I mean, it's exactly what you would intuitively do. Right? You have two vector fields. You go and look at every point, and at every point you take the two vectors of the vector fields at that point, and you add them in that tangent space. And from that, if you do this at every point, you get back your vector field. Okay, so that's clear. You find this addition. Now, slightly more interesting is this kind of thing that we might want to call an S multiplication, but now the question is over what field? And the answer is we can do something interesting. Before I write down from where to where this, well, let's not be so childish. So I can actually take not only a real number and multiply a vector field by a real number, I can multiply a vector field by an entire function on the manifold in the following fashion. Gamma Tm goes to gamma Tm, so that I take a function on the manifold and a vector field on the manifold, and I send this to something I call f circ dot sigma, where this is again defined pointwise, no secret here. So f circ dot sigma is a new vector field lying here, right? Defined pointwise, such that this is f of p times sigma of p, and this is obviously the S multiplication in TPM, right? Okay, so that's innocent enough, and of course the idea is you take one vector field, and now of course we can take a function which is at this point yields a different value than here, and I scale the vector of the vector field here with the value of the function as it is here, and I scale the given value of the vector field sigma at the other point by the value of the function at that point, right? There's no need to have one global real number doubling or tripling or whatever the vector field, but you have a function that can change from point to point. It's very innocent, okay, and it has dramatic effects in what follows, okay? So, and we recall that this C infinity M, this appeared in various forms so far. One of the forms it appeared in was as a vector space, where this was an S multiplication, and it was the S multiplication where every function could be multiplied by a real number and so on. You get a function back, smooth function. But that's not what I mean here. I here rather mean a big blob. I mean a multiplication between two such elements that made this thing actually into a ring. Okay? So obviously you can add two functions pointwise, and you can also multiply two functions pointwise. Okay? It's a different dot than the one in, that we equipped it with before, where you just get from it an R vector space. So maybe I should first write down with a little dot, and as such it's an R vector space. But we also, I think we already saw this, that you can at the same time or alternatively, if you equip it with a multiplication, to make it into a ring. Why is it only a ring? Well, what was a ring again? Okay, I'll say again in a second to be clear, but here it becomes a ring. And if you multiply two functions, it's no longer true that every non-zero function has a multiplicative inverse. It's enough, the failure to have a multiplicative inverse for a function is already there if the function has 1 0 somewhere, because then there is no other function by which you could multiply it so that you get back to the unit function that gives you a 1 everywhere. How would, clear. Okay, so it's a ring. Okay, so that means we have here a structure on the set of all vector fields that has an addition and has an S multiplication, but the elements here are no longer the elements of a field, they're only the elements of a ring. Now, one could think that this is not big business, but in fact it is. You can show that these two operations plus, circ plus, and circ dot, that they satisfy the properties Caney and adu, which is the commutative, associative, neutral element, and inverse element of this circ plus addition, and the associativity of the circ plus, and then the distributive laws are with the circ times and the circ plus and stuff like this, and the other distributive law distributes over the pluses in the ring and the circ dot, something like this. So these are the typical vector space axioms that you have, only that the underlying field is not a field at all, it's only a ring. So we could easily call this a vector space, that we could say that this field, set of all vector fields, can be given a vector space structure over a ring. Okay? Now, vector space structures over a ring behave so differently from vector spaces that they got their own name in order to not get confused. And that name is a module. Okay? So that's the motivation why we're interested in modules over rings. It's not exotic at all. It immediately comes up once you deal with tensor fields. I should add, of course, you could restrict here to having only real numbers. You say, well, if this gets us into mathematically deep subject, why don't we just restrict ourselves to only scaling vector fields with a global real number? We could do that. Well, the answer is then we would always get over-countable bases for such vector field sets, and that we don't want. I'll show you again why that comes up. Okay, so we definitely want to be able, I mean, roughly speaking, you want to provide coefficients for a tensor field where the coefficients are fields. Fields in a physical sense can change from point to point. That's how we understand vector fields. We say that's the coefficients of this vector field, and they change from point to point. Okay, and in order for the coefficients to be functions, that's what I mean. We want them to be functions. You need to have that. We'll come back to that later. Okay, so we definitely want this, and it's now worth looking at the algebraic structures behind this. So I said it before, but recall that a ring R with an addition and a multiplication, where again I emphasize the addition is from R cross R to R, and the multiplication is also from R cross R to R. A ring is a structure, is a set with two such operations, such that you have CANI. If it was a field, you had again CANI, and you had a distributive law. I think last time I told about that, I forgot to write down the distributive law. Well, you know that. It's a self-correcting mistake, I hope. Well, if you had a field, you had these laws, commutative, associative, neutral, and inverse. Here as well, if you take out the zero, that's the neutral element from here, then you have these laws there. And you have the distributive law that links the two operations. Now, for a ring, however, it's a special case if the ring is commutative, and we call a ring that has this axiom a commutative ring. So only for commutative rings, which implies you can leave it out and you still have a ring. It's just they're not a commutative ring. Now, the neutral element of multiplication, this is only in unital rings. So on rare occasion, one could think about rings that do not even have the neutral element in them, okay? But if they do, then we call this a new unital ring, and we will always only talk about unital rings. It's just for completeness here. And the inverse back here is also not necessarily there in a ring. but it is there, or if it is there, then we call the ring a division ring, only for division rings. So, if a structure that otherwise is a field fails to be commutative, the ring, it's no longer a field, it's a ring. Sometimes I think one then calls it a skew ring, a skew field. Anyway, or if it lacks the unit, it's still a ring, it's no longer a unital ring, it's certainly not a field. Or if not every non-zero element, zero being the neutral element from the addition, if not every non-zero element has an inverse, then it's not a field, it's not even a division ring, but it's still a ring. Okay? And these three things can be missing quite independent. Well, not quite independent of each other, because you see, you could never have a division ring if the ring wasn't unital, because it's the definition of the inverse that if you take any ring element that's not the neutral element here, there is another ring element such that the product yields this neutral element. So, okay, fine. Aha, so that's a ring, and so let's take our example. I mean, there are many examples that are of interest to mathematicians, but we're not going to go into that. Let's take our example, C infinity plus time. So it was the big blob, so that it is an operation like this one. So it's a multiplication. This is a ring. Is it commutative? So I take the blob, the pointwise defined product of two functions. I get a function. Is that commutative? Yes. Why is it commutative? It inherits the commutativity from the product in where? In R, right, in the real numbers. That's right. So it's certainly a commutative ring. Commutative ring, nice. Is it a unital ring? Is there a multiplicative inverse? Is there a function by which I can multiply any element in here and I get the element back? Yes. There is the unit function. So it's unital. So, and the identity on C infinity m is given by the function that to every point of the manifold assigns the real number 1. Right? Of course, that lies in here. That's a smooth function. So it's a commutative, unital. Is it a division ring? Can I find to every non-zero function, the zero function would be the neutral element here for addition, of course, can I find for any non-zero function another function such that the product is the 1? No, because if I have a function that's non-zero but gets 0 at some point, that doesn't make it the 0 in this space, of course. If I get 0 at some point, then there will be no other function that, in a sense, by pointwise multiplication, which this is, gets rid of the 0 to produce a 1 also at that point. Okay? So it's a commutative unital ring, but not, and that's of key importance, but not a so-called division ring. Okay. So that's the observation here. So we're immediately dealing with a commutative and unital ring. Okay, fine. So now comes the next definition, not much of a surprise, that m circ plus circ dot, which is now an S multiplication, is called an R module. So you see, not a K vector space, but it's called an R module. If the circ addition is M, so this M, there's some double working, right? Here the M is the manifold we're looking at all the time, the smooth manifold. And now I use M to denote an R module. You won't be confused, will you? I could choose a different letter, but M like module, that's very nice. Okay, so don't be confused. So the circ addition is M cross M goes to M. And the circ multiplication, well, it's an S multiplication, goes from the ring. R is a ring. Some ring, no further constraint. R is a ring, R cross M to M. Well, if you want to be very picky, you can say this is called a left arm module because the multiplication is from the left. You could define a right arm module where this multiplication by the ring elements is from the right. Then you could talk about an arm module if you have both and they're compatible. Let's not go into this, it's not necessary. We call this an arm module. Okay, so you can always make further distinctions. Okay, if you have these two guys and they satisfy, again, CANI and ADDU. But now, of course, for these operations here and so on. Okay? So it's a vector space, but over a ring. Vector space over a ring, and that would be perfectly fine terminology, but because they have such different properties from vector spaces occasionally, they deserve an extra name. That's all that there is to it. Okay. There's an R module. Okay. And as an example, that is what I provided as motivation. Example is the set of all vector fields on a manifold, set of all sections, equipped with their with the pointwise addition S multiplication is a C infinity M module. So the tricky thing in the module is not the module structure, it's the ring structure that underlies it. Okay, fine. So now the point is, what's the big deal about this being a module and not a vector space? And then the key fact is the following. Unlike a vector space, a module generically does not have a basis. Okay. It has a basis, so I say here, unless R is a division ring. So if the underlying ring is a division ring, meaning in the ring there exist multiplicative inverses for every but the non-zero element, for every non-zero element, then there's not much of a difference. Then, I mean, essentially then a module is by all means a vector space with all its properties. It's still a module because you could have a skew ring, for instance, right? You could have lack of commutativity in the ring elements, but that wouldn't be seen. I mean, it's of course seen. It plays a role in some calculations, but the structural properties of a module are then very much as those of a vector space. And actually, we're going to prove that. Okay, so that's important enough to prove it. But you see, the case of direct interest to us, namely the vector fields that are C infinity M module, C infinity M is just not a division ring. So this vector space, the space of the module of vector fields does not have a basis generically. And we will actually see geometric examples for that otherwise may be mystifying, but here you say, yeah, of course it doesn't need to have a basis because the module, I mean, how would it have a basis if it's a module over a non-division ring? So we'll look into that, and in particular, we're going to prove what I just asserted here. Well, we're going to prove the converse, namely, or the opposite, namely that every module over a division ring, in particular a vector space, has a basis. So we used this all along, that vector spaces have a basis. We can slightly extend this to every module over a division ring. So the commutativity of the underlying ring is not important, but the division ring property is. And then we can show every such module has a basis. And later we're going to understand the failure of our space of vector fields to have a basis as a failure of the underlying module of this module having being a so-called free module that has a basis. Okay, we're going to come to that. So this is now the abstract form rings and modules with the key example we're interested in. So now we're going to explore this formally. Well, maybe before I prove this, that every module over a division ring has a basis, I give you the counter example that you immediately understand. Okay. Okay, let me formulate the theorem, then I give you the counter example. Well, in the sense it's an example, and then I'll prove it. So the theorem is that if D is a division ring, then a D module V, we call it immediately V like vector space, but it's a module, right? A D module, because this D may be non-commutative, then a D module V has a basis. Corollary of this theorem we're going to prove, corollary, every vector space has a basis. Basis since any field, meaning numbers, underlying numbers, since any field is a division ring. So we also get that for free, that every vector space has a basis, and we're going to show it. So what goes wrong if there is not, if the underlying ring is not a division ring? Geometric example. For the case that the underlying ring is not a division ring. Well, let me give you two intuitions. The first intuition is assume that the manifold is R2, so the plane, the blackboard plane. And you consider a vector field on the blackboard plane. For instance, this one, a smooth vector field. Well, that's a vector field on the blackboard plane. Everywhere is a vector attached. Then gamma of Tm, although, or not although, being being a C infinity M module, I say coincidentally has a basis. But didn't I say if the ring is not a division ring, it doesn't have a basis? No, I never said that. I said if the underlying ring is a division ring, then you're guaranteed to have a basis, right? Well, if it's not, you may or you may not have. In this particular example of R2, every vector field, if you consider the set of vector fields as a C infinity M module, it has a basis. But what does that mean? That means there exist now not numbers, but there exist in this case two functions, two coefficient functions, right? Well, we should start here. There exists an E1, E2. There exist two vector fields, E1 and E2, not vectors, but vector fields, such that there exists, such that for every field there exist coefficient functions such that the entire field can be written as a linear combination of coefficient functions with a vector field. So how do you have to think about the spaces? Well, the spaces could be, in this particular example, this could be the E1 vector field. But then we also have an E2 vector field. So that's the E2 vector field. And doubtless, if I now look at an arbitrary, well, smooth vector field, I have to think about this being on top of this, or both of these vector fields extending everywhere, right? All of these three vector fields. Then clearly, if I have at some point, so let's say it looks somehow like this, okay, then obviously by choosing the right coefficient functions at every point, I can produce the blue vector field of the other two. But then I need coefficient functions. So these guys really need to be functions such that at every point I can scale E1 and E2 differently to get the blue result, right? That's clear, or not? That's fine. That's our standard intuition about the vector field. So you say it's all fine. It's all fine. Okay, it's not a division ring, but apparently there is no problem. So what is the issue? Well, the issue is in example 2. Let's say the smooth manifold is the sphere. And let's say I have a vector field V tangent to the sphere. Now my claim is, now the set of all vector fields being a C infinity of S2 of M, well, M is S2, module, does not have a basis. Well, here I should have said a basis means there exist unique such coefficient functions, right? Otherwise, it's only a generating system. But a basis is there exists a unique decomposition this way. Does not have a basis. Now, how do we understand this? And this is due to a famous result. Well, this is due to a famous and, in fact, very intuitive result. Namely, the result is called you cannot comb a sphere. I first give you the intuitive idea, and then I write down what it means formally. Assume you have a sphere, and at every point of the sphere, there is a hair. Okay? The sphere is a hairy sphere. Now, I give you a comb, and I tell you at no point has the hair length 0. I mean, we do this, right? We shave and we produce points on the sphere that have non-zero, I have 0 length hair. But assume I don't do that. I'm an ape or so. I'm fully haired, right? The whole sphere is hair. So now I give you a comb. So comb the head of an ape. Okay? Try to comb this in a smooth way so that then you put the parting and stuff. But at no point should the resulting vector field that's given by the hair that you now comb along the head, at no point should this be non-smooth. Can you do this? Can you do this? No, you can't. If you look here, right, so there is this curl, right? So there, if you comb a sphere, you will not avoid that at some point there is such a curl, and then you may go on here like this. Maybe you have to have another curl. Maybe you have to have a second curl. Okay, but at this point, the field is not smooth because if you take this seriously, here it needs to vanish. Okay, so if you have a sphere and the hair goes has constant length, for instance, and goes out, there's no way to comb it. Okay, you cannot do that. So technically, it means there exists no everywhere non-zero and everywhere smooth vector field on S2, on the sphere. Okay. Now, what does that have to do with vector fields on the sphere having a basis? Well, that means if we don't have one such vector field, much less do we have two. That means even if I start at some point with some idea of a basis, right, and maybe I can take this to, no, it looks like you can have a basis. You can have the orange vector field. You can have the white vector field, E1, and the orange vector field, E2. But already E1 cannot be everywhere non-vanishing and smooth. Also, E2 cannot be individually be everywhere non-zero and smooth. But a vector field, if it's supposed to be, or a vector, if it's supposed to be part of a basis, cannot vanish, right? So you see that this simple thing that already there is not one everywhere non-zero and everywhere smooth vector field, that it means much less are there two that can then be linearly independent everywhere, such that you could take an arbitrary vector field on the sphere and uniquely decompose it in terms of this basis, because it's not a basis. For instance, assume that this is the point where the, if it's to be smooth, where the E1 vanishes, and even if the E2 at this point happens to be there, and now you have a vector field, a blue vector field, that has not only an E2 component, but needs an extra component, well, the E1, for instance, cannot provide it. Okay, so that means there's no basis for the vector fields on the sphere. Now we understand. Well, here we were lucky, although this is a division ring, non-division ring, because of the special structure of R2, everything was fine. But on the sphere, we have an example where we have a module over a non-division ring, and indeed, it doesn't have a basis. Okay, so I think that's an important point. This is already, well, an illustration of the theorem we're going to prove. But are there any questions here? Please ask for clarification here if you got lost. Okay. So what if we come back to the idea, well, if this module of this ring structure here, non-division ring structure of the coefficients gets us into trouble, why don't we just withdraw and we say, well, but then let's just consider vector fields as a vector space over the real numbers, which they are. Well, then the problem is, okay, you can do this, and then you can maybe, you can certainly provide a basis, because a vector space has a basis, but then you see, for the coefficients in such a decomposition of a basis, you were bound also to real numbers, because it's only real numbers that you then can multiply with the elements. Okay? But then, very clearly, imagine, take this example alone, you have this E1, this E2, but this would no longer provide a basis, because this blue vector field could not be expressed in terms of E1 and E2 If these guys were just real numbers, then I could only, in this case, only express constant vector fields, where everywhere the blue vectors in the same direction, because at every point I would have to take the same linear combination of E1 and E2. Well, that we don't want. So then I would need non-countably many basis elements. Well, that becomes not tractable. Okay? So we really want the coefficient functions for tensor fields, but we have to deal with this situation. Now let's understand this situation algebraically. So that amounts to a proof of this theorem. If D is a division ring, then a D module V has a basis, and otherwise it might not, depending on circumstances. Okay. So the proof of the theorem requires some preparation. And if this proof wasn't so important, and if the techniques in there and the notions appearing in there were not so important and so ubiquitous in mathematics, I would probably not provide the proof. But so everything that now comes is of real importance. So the first thing is, I say here, since it requires the axiom of choice but in the incarnation of Zorn's lemma. So I say incarnation because Zorn's lemma is in fact equivalent to the axiom of choice if you have all the other axioms of Zermelo-Fraenkel set theory. Okay? And so it's just another way to express the axiom of choice. But Zorn's lemma comes in a form that's very often very useful. And so I write down Zorn's lemma. And you need to have some space around it. Okay? So here we have Zorn's lemma. I first state it, and then I explain the notions that appear in there. So Zorn's lemma is a partially ordered set. A partially ordered set, let's call it P. Partially ordered set is something I need to explain. Whose every totally ordered subset T, so I need to tell you what a totally ordered subset is, a partially ordered set P, whose every totally ordered subset T has an upper bound in P. So I need to tell you what an upper bound is for such a set. Has an upper bound in P, contains, now that's the verb of the sentence, so it obviously refers to the subject of the sentence, contains, this P contains a maximal element. So I need to tell you what a maximal element is. So it's very enlightening apart from 4 undefined terms. So what's the partially ordered set? A partially ordered set is a set P together with a relation less or equal to. But keep an open mind about what this less or equal to is. So this thing is partially ordered set, or is partially ordered if 3 properties are satisfied. The first property is called reflexivity, and that is that A is less or equal to A for every A in P. Okay, I don't, you get it. These are the elements in the set, reflexivity. The second is called anti-symmetry. So not symmetry like in the equivalence relation, but antisymmetry. And antisymmetry in this case is defined A less or equal to B and B less or equal to A. If both of this is the case, then A is already equal to B. If you think of less or equal to, this is kind of intuitive. Okay, but that's an abstract thing here. And finally, it's transitive. Well, that's kind of as expected. If A less or equal to B and B less or equals to C, then also A less or equal to C. But keep an open mind as to what the exact nature of this less or equal to is, because P is not necessarily numbers. And we'll find such an instance in a second. So you read partially ordered set, you think this. Aha, this P is a partially ordered set. Now what's a totally ordered set? That's simple. T, and I use the same symbol, is totally ordered if, again, three axioms are satisfied. So let's call them ABC to distinguish. The first one is totality. And totality is the following. That was one, well, it's maybe not clever. So okay, so we do not require reflexivity from the left. We don't require that. Second, we require antisymmetry. As before, I don't need to repeat this. 3, we require transitivity. As before, so I say no more about this. But then I have not an alternative, that's what I wanted to avoid. I have another requirement that has nothing to do with reflexivity. It's not the counterpart of reflexivity, it's just something new. It's called totality. And totality means that if A is less or equal to B, no, that either A is less or equal to B or, not either, okay, I again correct myself, inclusive or, that A is less or equal to B or B is less or equal to A for all AB in T. So that is, and I'll comment on that in a second, that is the notion of a set being not partially but totally ordered. And obviously, if something is a subset in particular, it's a set, and it can, as a set, satisfy these properties. What's the totality in contrast to the being partial here? Well, you see here, you could easily have two elements that stand in no relation to each other. Okay? Whereas here, the totality requires that any elements of the T, either they're related this way or the other way. Yeah?
And E numbers are partial ordered but not totally ordered.
Which numbers?
Not the reals, the complex numbers.
The complex numbers are?
Partial ordered but not totally ordered, for example.
Well, they're not ordered at all, are they?
But you said in partial ordered you don't need that everybody has a relation.
I see, okay. So you're asking, is it possible to establish a partial order on the complex numbers? That's a reasonable question. Well, certainly you can say, well, for instance, you could define, if this is C, you could say this only relates objects on the real line. That could never be a total order, because then any two objects would have to be related on the real line. The question is any number, and on the real line it's supposed to be the standard less or equal to, then reflexivity would be given, antisymmetry would certainly, yeah, there you're right. You're right. Okay, so example for a partial order on the complex numbers have only the objects on the real subset ordered with the standard less or equal. That's right. That's a partial order. And you see on the real numbers, it's a total order, if you only take the real numbers, because any two real numbers are related in this way. This is an inclusive OR, so it could be that it's at the same time, and then, well, it's even true that then it also satisfies reflexivity, but then it still is totally ordered. That's right. That's right. So that's the difference here. Okay? So far so good. This you need everywhere. Okay? That's why I bring it. So what's an upper bound in P? Okay. So an upper bound to a set. Okay. So U is an upper bound to a subset T in some set P if, well, for every element T in T, it's true that T is less or equal to U. And U can come from P. That's what we mean by it's an upper bound in P. There is such a U. Okay? And which sign is it this one or is it that one that I use here? Well, it's this one, strictly speaking, because I compare an element in T with an element that's in P. T is a subset of P, but if I only went to this, I mean, if this is a subset, of course, this may be inherited from here, but strictly speaking, it's the one from over here. Okay, so that's an upper bound. Totally ordered subset. Now we need a maximal element, and there we've got to be a bit careful. M is a maximal element of P if there exists no x in P such that M is less or equal to x. Now one might be tempted, again, this guy here compares elements in P, so it is this one, right? Now, the name maximal element may have prompted an alternative definition. That's why I said we must be careful. You say it's a maximal element if for all U in P, it's true that U is less or equal to M. And that sounds like, well, right, not, there exists not is a not in front of here. It can jump in, and certainly this relation sign is flipped. No, it would only be flipped if this was this relation for the total order, because a not in front of such a relation sign only can be flipped if it's always true that any two elements are related. But that is not given for this here. But this formulation of the same idea, however, is correct, because there is no such thing in P such that it's greater or equal to M, but that means there could be others in P that are not related to M, but simply have nothing to do with this partial order. Okay? So that's a subtle point. Well, as it's written here, it's correct, but when one reproduces this, one must remember that. I mean, inspection of what you wrote down. I mean, in my preparation here, I wrote it down the wrong way. I'm very honest, right? And then further down the road, I thought, I mean, something is terribly wrong here. It's not even related. And then, okay, here you have to find this formulation because you're dealing with the partial order, not the total order. Okay? So that's it. Okay? That is Zorn's lemma. And as abstract as it seems, we very often deal with such relations. And, well, the proof of Zorn's lemma I'm not going to provide, but I tell you that in ZF set theory, so that's Zermelo-Fraenkel theory, that's Zermelo-Fraenkel but without the axiom of choice. It is true that the axiom of choice is equivalent to Zorn's lemma. Okay. Okay. And in this form, it's useful to us. And we'll use it to show that every module over a division ring, in particular every vector space, has a basis. Questions? Yeah?
I got one question concerning the upper bound.
Yes.
Why does it have to be an element of U?
Of P.
Of P, yeah.
Well, yeah.
Because later on you require that it has a connection to everything in T, which looks to me like a lot like an element of T, actually.
I see your point. I see your point. So you say, if this is the guy from here and I require this, so either I also use the same trick as over here. Okay, what do I need later? Later I need, actually it will lie, okay, I think that at this point I would like to use the same trick, that I say it's an upper bound if there exists no T in T such that let me think for a second, please. 600 T such that U is need later on the union of only it's an interesting question, and unfortunately I cannot decide from our application because there the upper bound I think will lie within T. So this also can't be it. Okay, so very good question. Thank you very much. Thank you very much. I don't know. I don't know. Let's play it safe for our purpose at the danger of Zorn's lemma being a little more general. But let's kill this and let's talk about U being an upper bound. Thank you very much for the question. An upper bound of a totally ordered set T if for all T in T it's true, so that's then a U in T, it's true that T is less or equal to U, and that would be this less or equal sign. So let's see whether I run into trouble this way. But now obviously your formal concern is satisfied, right? You say, okay, if it's totally ordered, then any two are related. In particular, if the U is in T, and I can always relate it like this. Okay. Okay, hang on. Good, look. Let me draw a diagram. I think we can revert to what I wrote before, but I'll draw it. It's a very good question. It's good that we discussed this. Thank you very much. So assume we have a totally ordered subset T. This is T, and by an arrow I mean that, well, I actually mean that this relation holds. From this element to this element to this element, they're totally ordered in this way. Okay? Now, this is the subset T, it's totally ordered. Now assume the subset T is part of a bigger set, capital P, so this is only T. But now I have the bigger set P, and there the whole thing looks maybe like this. Okay, so the whole thing is P, and only this guy here, this is T. Do we agree that P has a partial order? Oh dear, we have to check this. I don't know, something like this, okay? Let's say P is a partial order, it's transitive and so on, but you see there are parts, this guy has nothing to do with any of these, there's no relation between this one and that one, say, but there's a relation between these are partially ordered and so on, these are totally ordered, okay, you see this. So now I said an upper bound of a total set T is, well, I could say this, according to this definition, the modified definition, this would be an upper bound of this totally ordered subset T, according to this definition. Now I revert to my original definition. So let's say no, it's a U in P is an upper bound of a, and this I should have said, of a totally ordered set T. That's fine. And I should now say a totally ordered subset T in P. That is something I should add. Okay? If for every T, now I can use this guy again, is this, and now you say, but hang on a second, who tells you that you can compare this guy to these guys? So if this is the U, I mean, obviously, according to this definition, this is an upper bound. This U is an upper bound to this guy. As much as this guy, according to the same definition, an upper bound here. Because if this is a subset, this blue one is just a restriction of this one on the subset. Okay? Now this is a U. Now imagine, and that is what you were probably driving at, if these connections were not there. And then you'd say, well, this is not an upper bound to these guys because they can't be compared to this. Right? If there is this connection, I can compare this one to this one because of transitivity. Right? But if it's not there, then this U is not an upper bound to the set, and you're absolutely right. But then this guy would still be an upper bound to this set. It's not a problem, it's a special case. That's what I want to say. What I modified, the modified definition, was a special case of this definition. That's fine. And so this is not an upper bound, fair enough. As little as this one or that one upper bound of this. But this definition holds. The only thing I need to say is an upper bound of a totally ordered subset, so that if I can compare one in there with another one, I want to compare all of them with that up here. And so they must be all in the set must be related to each other. That's why it needs to be a totally ordered subset. So I stick to my original definition. Happy or unhappy? Okay. The original definition wasn't bad. Yeah.
Don't you actually explicitly need U to be out of T or in
No.
T? Because then if it would have to be in T, you can't like convergent series or so.
I know what you mean. Yeah, yeah. No, I mean, the point is I want to have the freedom. I want to have the freedom.
That's why U has to be in P. If you would say it's
Yes, it can be in all of P. It doesn't have to be in the subset T. That's right. Yeah, I want this freedom. So this is certainly the stronger statement, if I extend it like this. So I didn't unnecessarily want to restrict it, to play it safe. And I hope, well, now I don't have to hope anymore because that's what I used. Okay, good, good. So there is no structural reason to modify this. But thank you very much for shattering my confidence in the definition. But thinking about it for another second, I think it's pretty clear that that's fine. Okay, so let's continue. So finally, using Zorn's lemma, we'll have the proof, namely that every module over a division ring has a basis. Very important result. So how do we do this? Well, in several steps. A. Start by letting S be a generating system. The module we already called V and the division ring we called D. Let S be a generating system of V. That is, every element in V, for every such element, there exists a finite collection, V1 to Vn, of elements in the ring, so you could say components, such that the element can be written V equals VA. I should call them E1 or something, E1 to En, and I'm sorry, I labeled them down. No, I was right. V up to Vn. I forgot something. For every element in V, there exists, I forgot that, I'm sorry, there exists a finite collection of E's in this subset S. So what's a generating system? It's a subset of the module. There exists such a finite collection, and there exist correspondingly many elements in the ring, such that any element in the ring can be written this way. Then you say, but hang on, you're already assuming a basis. No, it's not a basis. It's only a generating system, because I said nothing whatsoever about being this being a unique decomposition of this vector in terms of this basis. Okay, basis, this generating system. But in the set S, there must be a finite subset such that this is true. Now you ask, okay, you're going to prove that there's going to be a basis. How do you know there's a generating system? And the answer is S always exists, since, e.g., for instance, we could use S to be the entire module. If you use as S the entire module, then certainly for every element in S, you will find a finite set of elements of S, namely that one itself, for instance, and a factor in the ring. It's a unital ring, so division ring, certainly a unital ring, so that V equals 1 times itself. Okay, so a generating system is not a big trick, but it may be a fantastically huge generating system, namely the entire module. But that shows you can always assume there's a generating system. That couldn't be any different. Okay? But the question is, can you extract a basis from such a generating system? But first we take this generating system. That's the first step. Now the second step is define a set, a partially ordered set. A partially ordered set. Well, what is that? It is a P with a less or equal relation by, well, I need to define the set first. The set P is supposed to collect all the subsets of S. All the subsets of S. So use a sub in the element of the power set of the generating system. Such that U is linearly independent. Linearly independent. I remind you what linear independence was, simply because you mostly check this in finite dimensional spaces. In general, linear independence means every finite subset of U is linearly independent in the simpler sense. I leave it here. You have the definition before. So every finite subset of U is linear independent in the sense that you have a finite sum with factors, the whole thing equals 0. That already implies that the factors are 0. But this must be true for any finite subset of U. Okay. So you define this P and you partial order it by inclusion. So this guy is actually the set theoretic inclusion. It makes sense. So you take two subsets of a set. Now, what possibilities do we have? The two subsets could be such that one is contained in the other. Then they are related by this ordering. It could be you have two subsets that are disjoint, then neither one is contained in the other nor the other in the one. But it's not a problem because we only need a partial order. That's fine. Okay, that's it. Okay, partially ordered by inclusion. That's the set P. Now, the next step consists in defining a totally ordered subspace, or rather take any. Let T be any arbitrary, any totally ordered subset of P. So P contains subsets of the generating system. Okay? And T is a totally ordered subset of P. That means it also contains elements of the power set of S. But now I require that they're in a total ordering relation to each other. And I don't tell you which ones I take any totally ordered one. Okay? And it's important that it's any, because we want to use we make no further assumptions. That's the point. I'm not going to tell you more specifically which T, because we want any such T in order to be able to apply Zorn's lemma. Because that says for a partially ordered subset whose every totally ordered subset T. So I cannot provide any further constraints here without being impaired to use Zorn's lemma. Now, if this is any totally ordered subset, then it immediately follows that if I take the union of all these elements in T, this will be an upper bound to T. Because obviously, everything that's in T is also in the union. Every subset in T is also in the union of T. So the union is an upper bound to T. And it is a linearly independent subset of the generating system. Why? Well, because every T, the T's were subsets of P, and in the P we are only linearly independent sets. So it's an upper bound to T, and it's linearly independent. So from this, it immediately follows, by virtue of Zorn's lemma, that P has a maximal element. There could be several. Call one of them B. So it has a maximal element, and so the existence suffices, and that one we pick. And this picking has to do with the axiom of choice if you look at Zorn's lemma in the proof of Zorn's lemma from ZFC set theory. P has a maximum element, call one of them B. By construction, B is a maximal with respect to the inclusion sign, in the sense biggest in that sense, in the inclusion sense, is a maximal linearly independent subset of the generating system. Aha, so what have we achieved here? We started with a generating system and we wanted to make a basis from it, okay? Now, what is missing to have a basis? Well, what's missing is that the elements, I need to pick a selection of elements that's large enough to still generate, but that is a linearly independent set. So now what we got is a maximal linearly independent subset. So it's linearly independent, and you cannot add anything to the set without losing this property. Okay, it's maximal. So that comes to step, I don't know, D. The claim now is, on the merits of what I showed before, is that the generating system is already generated by the elements in B. So I don't know how to write this. This is the span with coefficients from D of the B. And of course, by span, I mean any finite, as always, linear combination of elements of B, and I write capital D linear because the factors come from the division ring D. So my claim is this maximal linearly independent subset of S, which is guaranteed to exist by virtue of Zorn's lemma, already spans the entire generating system. It's linearly independent, so that already looks very good. So how do we show this? Or questions so far? Okay. So how do we show this? So proof within the proof. So since B is maximal linearly independent subset, that means that if I take B and so I start with let V be an element of the generating system. I want to show that every element in the generating system is spanned by B, so I take an arbitrary one. Let V be an arbitrary element in the generating system. Now, since B is maximal, it means that if I take this element V and I add it to the set, so I build this union, then this set, of course, includes B. Right? But that can't be because B is maximal as a linearly independent subset. That means I add this, then this set is no longer, or is linearly dependent. Linearly dependent. Why? Because B already was a maximal linearly independent subset. Okay? So it's linearly dependent. What does that mean? Linearly dependent, that means, so what is linearly dependent? That means there exists let's call them A1 to AN. I need to start differently again. Okay, I'm sorry. That means there exists E1 to EN in B and there exist A1 to an in D, but there also exists an A in D such that the sum AI EI, or we don't need the sum sign, such that this guy plus B times V is 0 and not, because it's dependent, and not all of A1 to AN, but also the A, not all of these n plus 1 numbers vanish. Again, is this true? Okay, we have a set that consists of all the elements in B and an extra element V. Okay? Well, you see, there is this issue. Assume this V was already in B, then this would be still linearly independent. Okay, so this is this thing of basis stuff. So this B is still totally ordered because it was the union of these totally ordered ones. Actually, it's more like a sequence. There are all these elements in B, and then I also take more like as a pair. I take in addition this guy. So it's only very loosely speaking that we say we build the union. Because you see, you have two vectors, V and V. They are linearly dependent. Is that right? But if I say I look at the set VV, then, well, that is just a set V that's linearly independent. Okay? So actually, we shouldn't say a basis is a subset. A basis is more like, well, if it's countable, it's like a sequence, right? You have an order. Things can appear double, but if they appear double, then you lose the linear independence. It's, I leave it like this, but it's more like a notational issue. No? I mean, it's also if you have a basis in other places, and you say the first component, the second component, the third component of a vector, well, then you need to have an order in your basis vectors. You cannot just exchange them. So again, the basis can actually not be a subset because a subset doesn't have an order. You know what I mean? So, but don't get confused by this. So we have the set B, and these elements in B, and we take the elements, the element V on top of it. V is an arbitrary element in the generating set. And we know this must be linearly dependent because of the maximal property of the B, guaranteed by Zorn's lemma. But that means that if I now take an arbitrary combination of elements in B and this V, right? And I build the sum, because linearly dependent, I can have this vanish without all of them having to vanish, namely not all of them vanish. Okay? Good. Aha. So, now, it is clear that this B, I should call it A. Okay. Such that this A, now it's clear that this A is certainly not 0. Why is that? I mean, not all of them vanish. That means this could be 0 and one of those isn't. Okay? Hang on, why was that? It's clear that this is non-zero. Ah, yeah. For if it was, if we had A equals 0, then it would immediately follow that AI EI is 0, and not all A1 to AN are 0. Because if this is 0, then one of the others must be non-zero. But this is in contradiction to the EI being a finite subset of a linearly independent set. This is a contradiction to B being linearly independent. So there's only one conclusion, that is that this factor in front of this extra element must be 0. Must be non-zero. Aha, and now it comes. But then, since this non-zero A being an element of a division ring. And it's a non-zero element, that means there exists a multiplicative inverse in D. Okay? It's non-zero. If we didn't have a division ring, that wouldn't mean it has an inverse. But in a division ring, it does. Aha! So then we can go back to this thing that's true, namely this one. We know A is non-zero. Therefore, we can take our arbitrary element V in the generating system we had. We can write as minus A inverse times AI EI. So I multiply every of the coefficients AI with the inverse of AI. Take this to the other side because the additive inverses exist, and I can express this arbitrarily chosen V in this fashion. And these here, E1 to En, are just a finite subset of B. Well, this is nothing but the statement that S is spanned by B, because any element can be expressed this way. And this is where we use the division ring, and hence this is an important condition in the theorem. Where were we? DE. But now it's also clear that the entire vector space is certainly spanned, not vector space, I'm sorry. The entire module over the division ring is of course spanned by its generating system. Well, that's the definition of the generating system. But the generating system is spanned already by this maximal linearly independent element B. Well, but that means nothing, but B is a basis for V. And it's really only a basis, as much as Zorn's lemma only guarantees you there is a maximal element. There may be others. Well, it's a basis, it's not the unique basis, of course. Didn't expect a unique basis. This is a basis for V. And that concludes the proof of the theorem. And again, every field, number field, is a division ring, hence every vector space has a basis. So this is now, every vector space has a Hamel basis, because this whole construction, you have maybe these infinite sets, but then you say there's a finite subset such that it can be spanned, that appears again and again. That's, of course, all for vector spaces without further structure, in particular without a topology or a norm. Every vector space has a Hamel basis. But more generally, every module over a division ring has a basis. But once again, after the proof, the reminder, but C infinity M is not a division ring, and hence gamma of 2M, all smooth sections of the tangent bundle, or in vulgar speech, all vector fields, gamma Tm considered as a C infinity M module is not guaranteed to have a basis. And a case in which it has a basis is the vector fields on R2. A case in which gamma Tm does not have a basis is the vector fields on the 2-sphere. So we have now reached a point of sophistication in this that we're no longer surprised, right? So if you think of vectors and vector fields and so on always in terms of its components, you get this illusion there are always components. But components refer to a basis, right? So in the case of vector fields, if there's no such basis, there are no such components. That means you need to stop thinking of tensor fields in its most general form in terms of their component functions, because there are no such component functions in general. Full stop. Okay? Hence, so before it seemed almost like a lot of formalism for formalism's sake, but it's really not so. You cannot think of a tensor field in terms of its component functions. Locally you can, okay? Locally you can say, okay, take only a patch of the sphere, and then of course, yeah, they're component functions, and that's what we do all the time, but maybe we have to change chart, and then we have component functions on each chart. That makes sense, but there is not necessarily a global component function. And that has nothing to do with choosing charts. It's also abstractly, there are no such things. Okay, now let me make a few more remarks on terminology, because it emerges here. Terminology. A module over a ring is called free if it has a basis. Now that doesn't mean that the ring needs to be a division ring. We saw an example, so e.g. gamma T R2 is free. The vector fields in R2, that set is free. It has a basis. But gamma of TS2 is not free. Okay, this is just terminology, right? A module that has a basis is free. So we could reformulate what we said before, is that unless R is a division ring, it's not guaranteed that a module over it is free. Sometimes it is, sometimes it isn't. That's a free module. Now, you can think about free modules in terms of so-called exact sequences and split exact sequences. I don't want to go into that, but then a free module has a certain property in terms of such sequences, but it's just a special case, and there is another type of module that shares exactly this property of free modules, but that property doesn't fix you to a free module. Anyway, that's a lot of talk. We may come back to that later in terms of cohomology and so on. But what you actually get here is that there is a notion of a projective module. A module, and I'll express this projectivity property in a simpler way, equivalent way. A module over a ring is called projective if it is, so a module, let's call it gamma, over a ring is called projective, if it is a direct summand of a free module. Let's call the free module F. So what I mean by this, it's a direct summand, it means there exists another module Q, module over the same ring. So if this is the ring R, this is the ring R, it's another R module, such that this gamma plus this other R module is a free module over this ring. Okay, and so then this guy is called projective. Now clearly every free module is projective, so remark, free implies projective. And indeed, as I remarked before with this mysterious remark about exact sequences, projective modules are kind of a generalization of a free module. Well, maybe I should also write another remark here. If an R module F is free, then as a module, it's actually isomorphic to the direct sum, I write R, well I want to write R but without the double line, to a direct sum, well if a finitely generated, I should say, if a finitely generated R module F, you see we don't have a basis, well in the free case yeah, okay. Finally generated module is free, then it's actually a direct sum of copies of the ring. Well, it's exactly like for vector spaces, right? In vector space, any finitely generated, I would say finite dimensional vector space, is a direct sum of the dimension many copies of the vector space, and so it's here a direct sum of the underlying ring. And you know that the direct sum, you know this from the problem sheet, is actually a Cartesian product if you think about it as a set. And then the plus means, well, it's equipped with a vector space structure that works component-wise, a linear structure that works component-wise, and it's exactly the same here. Now, a projective module fails to be free because only if you add another R module to it will it be a free module. Okay, there's a failure to be free in a projective module. And the question is, why do I say all of this? That's because we quote the theorem, and that's by Serre, Swan, and others. The extensions are by others. And well, it roughly says that the set of all, well, let's write in words. The set of all smooth sections of a vector fiber bundle over a smooth manifold M. What's a vector fiber bundle? Well, it's a fiber bundle where every fiber is a vector space, in particular the tangent bundle. But it could also be a cotangent, the cotangent bundle, because every fiber is then the cotangent space, which itself is a vector space. It could also be a tensor bundle, where at every point you attach a tensor, okay? But every tensor space at a point is a vector space, so every fiber is a vector space. So it's very general, right? Smooth sections of a vector fiber bundle over a smooth manifold M. This set is, well, the set is a finitely generated projective C infinity M module. That's it. So although it may not have a basis, and this module we usually call gamma of, well, capital E, where this E is the vector fiber bundle with projection down to M, right? But it's important to say it's finitely generated and it's projective. That is, gamma of E, so like gamma of Tm, for instance, in direct sum with some Q other C infinity module. So this is also C infinity module, C infinity of M module. This is a free vector space, free module, which very much behaves like a vector space. Now, if Q could be chosen to be empty, or, well, let's say the zero, the module with only the zero in it, the additive zero, okay, then gamma of E would be free. So, for instance, the gamma of the tangent bundle of R2, that was free. But the gamma of the tangent bundle of the 2 sphere didn't have a basis. It wasn't free, so there is a Q that makes it different from being free. So that means, so the theorem says this, and this is now the conclusion, so, well, corollary if you want. So this it is a corollary. It means this Q here quantifies of how much, or quantifies how much gamma of E fails to have a basis. Okay. But since this is just a module over a non-division ring, we didn't expect it to have a basis. If it has, fine, it's an accident, it's a coincidence, but normally it wouldn't have. So if somebody is surprised that there is no basis for the vector fields on a sphere, you can in future say, well, why would it be? It's just a projective module, it's not free. Okay? So it's the algebraic expression of this geometric fact. But of course, this doesn't only apply to the special example of the sphere. It's a quite generic thing that you cannot expect to have a basis there. So please allow me to wrap up with two more remarks. So we have another theorem that says if P and Q are projective modules, and let me put the projective in brackets because you can read this theorem with and without the projective. P and Q are projective modules over a commutative ring. Now, all of a sudden, I worry about commutativity, but I do not worry about a division ring because it's not our case anyway. If PQ are projective modules over a commutative ring R, then the set HOM R P Q, what is that? That's the set of all linear maps from P to Q. Linear. And linear is, of course, still defined as it was for vector spaces because you have this linear structure in the module. And it's R linear. So it's linear with respect to this ring. Then this is, again, a, in brackets, projective. And I should also say, if they are finitely generated projective modules, then this is again a finitely generated projective module. So the only surprise in here, if I hadn't emphasized in one of the previous lectures, is this commutative. Why do you need the commutative? And the proof goes straight through, well, and you equip this with the pointwise addition, this HOM R. The proof goes straight through, but you need for a dot, so you equip this with a dot plus and a dot S multiplication, right? If you take this and you multiply here by a ring element, then you can certainly, because of linearity, you can pull that ring element out, right? And then certainly because of associativity, so that's linearity of phi, and then because of associativity of the dot, you can write this A times R, and this is the multiplication in the ring dot phi of V, but you need to get this to the form R times A times phi of V in order to get it to R dot. Okay, now we have various dots. Oh dear, you get this. This is the factor here. That's fine. This one would just be a dot, but it's not the other dot. It's this dot in the Q module, I think. Now this back here, if I write of V, that's the one I want to define again. But this one is the one in Q again. And that's what you want. You want this to be times A phi of V. Exactly, there it is. In Q, I wrote the same thing twice, not very meaningful. Anyway, you want this so that you can conclude that you can pull this really in front and not just in the middle. You need to have this commute. So this is because of commutativity on the ring, right? Because this commute, oh, dangerous, this commutes, okay? So only over a commutative ring do you have this actually expected structure that the homomorphisms again are a structure of the same type. And what's also preserved is the projectivity and the being finitely generated. And in particular, we can look at HOM over C infinity M, which is a commutative ring. And we can start in our, well, let's not be too general, although it's true. We can start with our vector fields, and we can send them to C infinity M, because that is trivially a module over C infinity M. And this thing, again, is a finitely generated module over C infinity M, and gets, of course, the name gamma Tm star. Okay, it's the dual of this guy. And in fact, one can show that it is the sections over the cotangent bundle. So that closes the entire loop. And once we have that, we of course prepared, now fully prepared. Although if you're not fully prepared, you're not prepared. Anyway, now fully prepared to have the standard textbook definition a tensor field T on a smooth manifold M is a C infinity of M multilinear map T that takes you from, I should say a PQ or an RS tensor field that takes you from R copies of gamma T star M R times, and correspondingly S copies of gamma Tm to the ring. That means to C infinity M in a multilinear fashion, where the factors, however, are allowed to be elements of this ring. So what is a tensor field? Very simple. A tensor field of valence Rs eats up R covector fields and S vector fields and makes of them a function on the manifold. Of course, you can think of this pointwise. You can say at a given point, a tensor field takes R covectors, namely the covectors that define the covector that are defined by the covector fields you give in, and you take S vectors and you get back to the real numbers. But you do this at every point, so you get back to the functions. But that everything is smooth, that you get back to the smooth functions, and that the multilinearity is smooth, and that all that works together is because you have a C infinity M multilinear map. But now this whole thing here you could call the tensor, the space of all tensor fields, and it would again be a module over this ring. And obviously, if you talk about multilinear, if you eat covector fields and vector fields, and you talk about something that eats them, a tensor field, being multilinear, it must be multilinear with respect to the underlying ring structure. That makes perfect sense. It's just the multilinearity in this module. There is no, so my point is the following. This is written in textbooks and sometimes said, well, it's not R multilinear, it's C infinity M multilinear, and that needs to be checked. That's the key thing to check. But it must be C infinity M multilinear, because otherwise the whole thing doesn't make any sense. Okay? You need to have this because of this structure. So finally, we're back to a textbook definition, but we now see the module structure lurking underneath. And never on Earth would we get the idea that this guy here, the set of all tensor fields, should themselves have a basis. Because not even the guys you eat have necessarily a basis, because all of this is a module structure and not a vector space structure. Okay, but keeping that in mind, we can of course locally always work with a local basis, but just not with a global basis. Okay, so that's full circle. That's the relationship of modules and vector fields and tensor fields in general. That concludes this part of the lecture. Thank you very much.